Howdy, everybody. Thanks for the introduction, James. My name's Ian. I'm a staff engineer at Datadog. I originally worked on this presentation and a lot of the work I'm talking about. I did in close concert with my colleague, Isabel. She's unfortunately unable to join at the last moment, but had a huge hand in all of this, and excited to be able to present both of our work on her behalf as well. So talking about generally elevating cloud defense is generally how we think about doing large-scale, non-disruptive, fleet-wide migrations within Datadog, and kind of using the specific instance of how we migrated away from AWS IMDSv1 to IMDSv2 across our fleet, non-disruptively, safely, and in a fun way. Cool. So let's look at a couple incidents. There's a lot of security incidents in the world. I'm going to focus on a couple. One is looking back at 2019. We see a breach at Capital One. It leads to the exposure of customer data for over 100 million users across multiple countries. We start to see some words in the security reports of these, SSRF, IMDS abuse. We see in 2022 on HackerOne, a security report that has scary words in it like Department of Defense, but also has those similar sort of IMDS or server-side request forgery terms in it. And still, through now to 2025, we see articles from vendors like AWS talking about campaigns that target, sorry, this is from F5, campaigns targeting Amazon EC2 Instance Metadata Service via SSRF. So what these all have in common is the acronyms SSRF and IMDS, which means server-side request forgery and Instance Metadata Service. Like many attack vectors, the ways to mitigate this is sort of multifaceted and multi-layered. And a lot of times, as infrastructure grows, as the world evolves around us, we have to take infrastructure as it exists today, adapt it to current and new changing either threats or risk models, and sort of upgrade it in place safely to deal with these things. So using this sort of as a lens for how we, like I said, how we approach migrations, I'm going to be talking a little bit about why is IMDSv1 a security hazard, or really, like, why do we even want to use IMDSv1 in the first place? We'll talk about how we can deal with the security hazards that I'm going to talk about, and then we'll talk about how we get off it onto those presumably better solutions. And last at the end, I'm just going to synthesize up a little bit of sort of, here's the sort of patterns or lessons we see from doing this and from other similar things within Datadog. IMDSv1, why is it a hazard? Better first question might be, what is IMDSv1? IMDS means Instance Metadata Service. It's something that we see first emerged from Amazon Web Services, or AWS, in the mid to late aughts. It's a magical little server that when you make a virtual machine in Amazon Web Services, they mount a link local IP address listener, so only processes on that host are supposed to be able to read from it. And it just tells that host things like, what region am I running in? What version of the machine image am I using? Maybe what size or what instance type am I? But also, this nice little part highlighted in red, it serves as identity credentials. So in distributed systems, you make a new virtual machine. Most virtual machines are only useful if they're talking to some other system. And to talk to other systems, we generally need to authenticate and send them some form of credential to prove who we are. But important in all this is you have to have a first credential, a first thing that proves I am this virtual machine, or I am the Rocky service. And the way that sort of identity inception happens in modern distributed systems, one of the most common patterns is using these IMDSs. Rather than saying I spun up 100 virtual machines, I'm going to SSH to each of them and load an initial token that they use to talk to our identity providers or other services. That requires sort of out-of-band access, out-of-band orchestration. Instead, what we tend to see in AWS, GCP, Azure have similar mechanics. Other systems tend to evolve similar mechanics of the orchestrator puts this magic little listener on a link local address or a local host address, and things on that host can call it. And so the orchestrator's like, yeah, I know what this host is. I can give you the right credentials, and you can then go use those to get things from S3 or talk to other services. So yeah, a little more literally, you go from curling this IP address, 169.254.169.254, for what's my instance type, to maybe give me security credentials that are tied to the identity and access management instance profile tied to this virtual machine. And I'm going to focus mostly on AWS, but very similar patterns across most cloud providers. You get back some access key ID and some secret access key that you can then use to prove your identity. From a UX point of view, this is stellar. We have short-lived tokens. We aren't using long-lived tokens that we have to manually orchestrate. All of AWS's SDKs and CLIs automatically know that if you aren't feeding them access keys, they're like, that's fine. I don't have credentials. Let me just check the magical little IMDS and get them from there. So your users aren't handling credentials, which means they're less likely to put them in logs. They're short-lived. Everybody wins. It's a great, great, great system. I think one of the bigger sort of evolutions of credential and access management and distributed systems over the last few decades. There's one catch. I mentioned that it's a server listener. I mentioned that the host doesn't have any prior credentials. This is how we get our first credential. This model relies on the fact that only processes that you intend to run on the host have access to this listener. This is a problem when you get into a class of attacks that are grouped as and usually talked about as server-side request forgery. And all server-side request forgery is you probably have lots of services in your infrastructure that receive input from users, process that in some way, and then make API calls to other services. If the user input can change the URL that you use for later calls to downstream services or change the information you send to them, attackers can sometimes manipulate maybe even the underlying HTTP client you're using or your own logic to trick one of your services into making a different call to a different service. In this case, like a trivial example might be, without getting too clever even, is using mechanics like HTTP 301 redirects. You can redirect a GET request to another URL, and if you're able to get a server to cause a server to redirect itself to maybe a local host URL, maybe the local host URL I was just talking about, and have the server fetch some credentials from that local host and then return it to you as the attacker, you now have a set of security credentials that, sure, they're ephemeral, but you're able to start doing things as that host from outside of that infrastructure. SSRF attacks exist constantly and all over the place. There's a series of mitigations that can work on them, but we see them happen consistently in a lot of ways. I think if you sort of imagine 10, 15 years ago, when there's a lot of SQL injection attacks, because we have a lot of sort of monolithic apps where you have one app in front of one database, SSRF attacks, I think, are sort of a natural evolution of that into a world where you have a lot of microservices and different things. Instead of injecting context into the SQL query, you're just injecting context into a downstream HTTP call and using that to manipulate things and get arbitrary results back. I've been talking a lot about EC2 hosts in AWS and sort of generally waving at virtual machines from any cloud provider. A lot of people in the industry now run things on Kubernetes or Elastic Container Service or other containerized things. Is this combination of IMDS and SSRF a problem for those? Absolutely. For things like ECS, Elastic Container Service, and EKS, AWS's managed Kubernetes solution, they use the same IMDS APIs and services for delivering credentials that EC2 uses. So absolutely the same vectors there, same challenges. Self-hosted Kubernetes applications can absolutely be a problem too. You see open source things like kube.am, which emulates the IMDS service and runs it within your Kubernetes infrastructure so that your pods sort of think they live within AWS, or things like Attache, which is an open source version of what we use internally at Datadog for a similar thing, which is emulating IMDS services. So we get all that great stuff within our pods where those AWS SDKs and CLIs just work out of the box and think that they're running natively on AWS. But it uses this same channel that is vulnerable potentially to SSRF attacks. Every V1 is begging for a V2. In this case, AWS recognized that there were SSRF challenges particular to the way IMDSv1 was implemented. I mentioned that we see this IMDS pattern emerge first with AWS and first in the aughts. It's one of the earliest. And so you see some things in later implementations like GCPs that start to be aware of these things. AWS didn't have the benefit of hindsight of their own implementation. They were one of the first, and so we discovered a lot of these things through that implementation, which means to address it, they had to introduce a V2. So let's talk about V1 versus V2 as a compare and contrast. IMDSv1 uses a GET request to an endpoint and just returns the credentials. Common things we look for in SSRFs are, I mentioned HTTP redirects are a really easy way to send a GET URL somewhere. You don't have to, with this, you can do that. You don't have to send a particular request body. Another thing we commonly see as SSRF hardening is specific headers. It's often much easier to manipulate an application into modifying the request payload or the request URL. Getting arbitrary clients that someone put in a microservice to add specific headers tends to be more difficult. Not impossible, and almost everything I'm talking about is in the realm of more difficult versus impossible. but it's sort of through layering up more difficulties in multiple places, it becomes effectively challenging, if not impossible, to exploit. So IMDS1, no specific headers, nothing in the request body. You really just need to trick a server into sending a single GET request to a specific URL, and you're good to go. IMDSv2 addresses this not just by adding a header about halfway down that has a specific header that's going to be hard for someone to inject, and by using a put in its initiation request. It's, again, much harder to, it is more difficult to get clients to do put or post requests than gets in SSRF attacks generally. It combines those with a session-based approach, and so if you're a user who's using it as intended, your client's going to make one request to put. It says, hey, AWS IMDSv1, start a session. And AWS IMDSv1 says, cool, here's your token, 1, 2, 3, 4, 5. It's probably not a serial number, it's randomized. But, and then you send that on subsequent requests. And your IMDSv1 server says, yeah, I remember creating a session called 1, 2, 3, 4, 5. It's in your header. I know that this is probably the local user agent and not someone external inducing the action. If you're an attacker, on the other hand, you now no longer just have to trick the client into making one bad request that's a GET. You have to trick the client into first making one request to get a session token or leaking its current session token, and then tricking it into making a second specific request with that header to use it. So sort of the attacker has to catch you goofing twice, which is always good. It's much easier to goof once than it is to goof twice. In table format, just to summarize, IMDSv1 uses get method, much easier to do. There's no anti-SSRF headers. There's no network hop limits. I didn't go into depth here. IMDSv2 has some very cool stuff where it looks at the number of network hops taken by the client and in the routing to do it. And so you can say, don't serve any IMDSv2 requests that hop the network more than 2 times as another layer of mitigation against external requests triggering it. Yeah, so IMDSv2 does have those network hop limits. It does require a session-specific value for a header, and it uses the put method. Cool, so IMDSv2 fixed all our problems. We're all good to go, and as long as we use it, though. And even just looking at usage, how many things are, just using IMDSv2 is not enough. If 100% of your infrastructure is making API calls only using IMDSv2, that's great. But if the underlying infrastructure still supports IMDSv1, you're not really any safer. Like an attacker can still manipulate a client into calling that. And so what we see when we look across industry surveys and looking at various data sources is that the good news is roughly 50% of things we see running on AWS only allow IMDSv2, so they're good to go. The bad news, very much a cup half full, half empty sort of situation, is 50% of the infrastructure still allows IMDSv1 API calls. If anyone wants a fun exercise after the session, say IMDS like 8 times in a row quickly. It gets harder each time somehow. Cool. Yeah. So we know how to prevent these attacks. We know that we want to turn off IMDSv1 to get the actual safety of IMDSv2, because using v2 by itself is not really enough. It's turning off v1 that gives us the value. So yeah, let's just flip it off. I mentioned that AWS SDKs, one of the great parts of this is all their SDKs have built-in support for all of this. All of their SDKs years ago started automatically trying IMDSv2 by default and only falling back to v1. So it's probably pretty easy to flip off. That's wrong. That's absolutely not the case. There's a long tail of things that you can discover in your infrastructure that we discover in ours that maybe they could be using out-of-date SDKs. They could be making manual curl calls and shell scripts. So that if you accidentally flip it on, which is very much what happened with us, we picked up a change in a new Ubuntu long-term support image that we were rolling out. And we saw that in a small percentage of cases, but enough to impact our operations. Certain services were failing to get credentials to talk to AWS. And in this case, we had to work with Ubuntu to roll back that change and figure out how do we, 99% of our applications were fine with this, but how do we deal with that 1% long tail in a world where we need to turn it off everywhere to actually gain most of the safety? So digging into sort of the specifics of how we think about this at Datadog, sort of I mentioned flippantly, let's just turn the switch on. Generally for our infrastructure, that's not a recipe for success and not a good time for us on the infrastructure side, not a good time for our users, can be a bad time for our customers too. Because we run tens of thousands of nodes across hundreds of clusters in multiple regions. thousands of services, all of that sort of thing. And our fleet is heterogeneous enough that we have pretty good intuitions about how things will work. We use Datadog heavily internally to understand what the impact will be. But a lot of times, if there's a long but small tail, there's surprises for us. And we need to figure out ways to stage and incrementally evaluate changes and roll them out safely so that we discover those problems earlier and in smaller contexts before they turn into incidents or larger outages. A process that we use, and I say this, it's not in the sense that like you're not going to find a Jira ticket at Datadog that says like how are you going to find, fix, remediate, and prevent. This is more sort of a synthesized up like pattern that we see and not like a rigid process. But sort of a mental framework that I think is helpful for this and how we approach this is instead of taking as one big, large single migration, we know we need to break it down into small incremental migrations for each service, each chunk of infrastructure, and approach each of those through finding things, finding what things are going to be impacted and what needs to be fixed, fixing them, remediating them in the sense of making it so that we get, in this case, remediation is making sure that we're no longer using IMDSv1 on their chunk of infrastructure. And then prevent is adding additional layers so that, I mentioned goofing before, so that if we goof once and that first remediation layer, we have a rollback or something happens, we don't wake up 6 months from now and say, oh, we had IMDSv1 disabled everywhere. This one configuration unrelated to it changed, and now we actually see IMDSv1 calls happening in a bunch of places, and we can't just turn it back off again. And that's prevention. I'm going to dig into this talking about the EC2 layer first at a little more depth, and then I'll sort of pivot it to how we did it at the Kubernetes layer, where we used that emulated IMDS service before. But in practice, I think there's going to be a lot of rhyming and a lot of overlap between the two. Let's talk about EC2. We need to know what EC2 instances allow IMDSv1 usage, and we need to know what EC2 instances use IMDSv1. So good news, we can leverage a CSM. At Datadog, we happen to use Datadog, but fundamentally, any CSM that you're using can work for this. Or you can use AWS tools. AWS has an API. You can call it and call the describe instances calls and say, show me, using the HTTP tokens field, does this support IMDSv1 currently or not? The AWS call might be tedious if as your infrastructure grows from maybe 100 to 1,000 to 10,000 plus nodes. And that's where things like CSM can start to be really useful in terms of handling all of that data aggregation. But in all cases, you can go to the API, you can go to tooling, and that can start to give you a view of, is all of my infrastructure supporting it today? Are only some auto-scaling groups, things like that. But that's still only half the battle. We generally don't want to turn things off if we think they're going to break something. And the way we know in this case if it's going to break something is, are things on that host currently calling IMDSv1? If they're not, we can probably turn it off, and we're probably fine. So it's important for us to be able to look at that. And in this case, AWS provides a metadata no token metric that tells us exactly that. So we use Datadog pretty heavily at Datadog. We ingest that metric to Datadog, and I can get a view of these are the auto-scaling groups, or these are the services that are still using IMDSv1, and start to think about, for the services that aren't, can I just turn it off today? And then for the services that are, can I start to work service by service with those service owners to get it turned off? In this particular case, the find step is actually, I think, more fun in the fun sense of challenging, in that going back to that, there's not an authentication mechanism of which process on your host is calling IMDSv1, because that's how they get their first credentials. So we can see that a host is doing it, but we're probably running multiple processes. There's probably, like, even in the case of a Kubernetes node, there's probably a mix of daemon sets, some systemd stuff maybe. And we can see from the AWS metric, that the host, something on the host is calling IMDSv1, but fixing that requires knowing what the something is. It's a different story if it's upgrade the AWS SDK in this daemon set than it is if you've got a systemd in a daemon that's calling a curl command. Probably potentially talking to different teams, potentially working with different people, different PRs to different places. Good news again, though. AWS has tooling, the IMDS packet analyzer, that you can run on a host and basically say, can you show me information about these request details and who's calling it? Excuse me. This is great. It provides a lot of context. This is a little more challenging in that it provides a lot of unstructured context. If you're looking at 10 nodes, great, you curl them, you have a good time. If you're thinking about how do we do this fleet-wide and get to 100%, probably don't want to go through the entire fleet, SSH into each host, or shell in. and do this for each of them. So alternatively, you can use things like eBPF. eBPF is Extended Berkeley Packet Filter. If you're not familiar with it, you can think of it as somewhat safe-ish, hooks into the kernel that you can use to look at network traffic and other kernel events. And in this case, again, you can use any set of tooling. We happen to use Datadog a lot. We're able to use eBPF trace data to go from this thing is making an HTTP request, so that's causing some packets and things, to which specific process in the process tree is doing it. And that might help us identify, in this case, that it's coming from container D. And that's going to give us some namespace information that's important to us, as well as some container IDs that can help us trace what's actually making the call originally. Cool. Let's start fixing it. We found the 12% of our fleet that has it enabled, and the 6% of that, I'm making these numbers up, but that are still calling IMDSv1. Let's start fixing things. I mentioned that this might be across lots of services. A big part of our work is enabling engineers who work on the product-facing services to act with a lot of agency, to own the outcomes of their services. And sometimes for migrations like this that are more platform-oriented, what that looks like for us is going to them and saying some mix of, hey, looks like you're calling IMDSv1, still we'd like you to call v2. And if we start there, generally the reaction is, what is IMDSv1 and why do I care about it? It's not, and they don't mean that in a bad way. They just want to understand more, and they didn't come to the first 20 minutes of this talk like you all have, so they probably have less context. And so in practice, what we tend to do is start from a place of trying to fix it, which is we'll go in, there's a couple different calls, but it's a finite number. It's probably upgrading a library or a curl or HTTP call from a client. You can do things like grepping for 169.254 and get high enough signal rates that, like, if we can find it for 95% of the use cases and open a PR, even if that PR is wrong, we've got the engineers on the service thinking about the specifics in their code, and engineers are generally much better at picking up that context and telling us why we're wrong and how to actually fix it than if we just come and say, can you upgrade V1 to V2, in which they say, I mean, I could, but I have other things to do, and can you help me with this? So we just jump straight to trying to help them, and sometimes we're right, and we're able to fix it, and they say, this is cool, thanks, I'll merge it, send it out with my next change. And sometimes they say, I don't think that's quite right. This is what we should do. And we say, great, do it. And sometimes they say, is this going to break my service? And we unspool a little of the context and say, no, this is totally fine. And if it does, here's how we roll back. Skip some bits on the service owner bit, which is we have a lot of service owners, so we have to find them. This is a place where we have this pattern, whether it's for vulnerability management or knowing who to page. Knowing who owns a service and who to talk to is really important in keeping that sort of, I mentioned a high agency, like people owning their own services culture. But as we've grown, it's gotten really important for us to make sure it's easy to find who owns the service and make sure you get the right two humans talking together quickly. Configuration management databases can be great for that. We happen to use the Datadog software catalog. We have all our services in there, and we go in, and there's links to here's the Slack channel of the owners, here's where to talk to them. Works really well for us for that. Remediation. Cool, there's a lot of ways to do this. One is you can update EC2 hosts. We talked to the service owner, they stopped making the IMDSv1 calls, they rolled out their code, we saw in those metrics, we all feel really good, both on the platform and service owner side, at turning this off. We can start by turning it off on a running instance using the AWS API or the CLI that's calling it. This is really great in that we can do it very quickly, we can do it very directly. It's less great in that it's not persistent. We're just turning it off for that host, and when we replace that host, inevitably in an auto-scaling group or things, the new host will not have that fixed. So this can be really good for testing and helping us build confidence that it's actually safe to do. But we also need to do it at creation time. We do a lot of things that are either infrastructure as code or orchestrated as direct nodes or auto-scaling groups. All of those support various options provided by the cloud provider. In this case, it's adding these two lines to, say, a Terraform module if you're using it. This doesn't fix your existing EC2 instances. It may or may not be an issue for you at the moment. But it does mean that all new instances deployed with this infrastructure is going to be safe and use IMDSv2 going forward. Putting some of those ideas together, how we did it in practice, we updated the configuration of the auto-scaling groups, like I mentioned. That gets our new instances. We're good to go. We regularly rotate all of our fleet continuously to pick up various security baseline patches and to be able to assert that everything's been updated within a certain number of days. So that means that once we've updated the auto-scaling group, we can say that within that number of days on that cadence, we'll have the rollout everywhere. And within that same sort of rollout management and cadencing, we have things where we can do like tagging instances to basically say this instance needs to be rotated more quickly. So generally, though, we were looking in terms of a number of days where we'd say this group will be safe in a number of days. This is a good balance of getting the security fix in to reliability. If we had more urgent things, though, we could tag them and say rotate this one sooner. What this looks like, so sort of from top to bottom, you can see that initially that large group of things is really a small number of use cases where we need to make a small number of changes, but they were widely used. And what we see is the number of IMDSv1 calls from Kate's nodes drops precipitously. And then you see around a little bit later, we start to enforce node group controllers, referring to how we manage some of our auto-scaling groups. And you can see that I think one of the things I like the most about these slides is you can see where we start to very slowly ramp up. That's us gaining confidence on use cases we know better, where we know if they break, we're probably the team that's getting paged anyways, or we think they're weird in ways that we want to learn how they break sooner. And then you can see us gain confidence and pretty quickly ramp up. And then you see us hit kind of the other side of a classic S-curve, which is there's some weird things that they're either weird technically or they're weird in that we found the right team, but they're actually not familiar with the service, is a little older, they're a little busy, and they say, look, could I look at this in 2 or 3 weeks or whatnot? And one of the things I like about approaching this incrementally is it puts us in a position to say yes to that. We care on the platform side that we're continually, that this line is going up. We don't care that every single person is working on it right now. Our goal is to make Datadog safer over the course of the next month or 2 months, meet this target. If 1 out of 10 teams is really busy right now and needs a little extra time, if 9 out of 10 teams are still making progress, we're in a good place, and then at the end, we can work more hand in hand with those 1 in 10. So that's kind of what you see at the end. And then finally, you see a sort of trail right behind it, a gradual cluster by cluster enforcement. Cool, prevention. This is really just so we've sort of enforced it at 1 layer, but we don't want to see regressions. It's just a huge bummer to do all this migration work and then 6 months later find out that actually you have started allowing IMDSv1 calls, and like mushrooms in a forest, people have started making IMDSv1 calls again. Because then you have to go talk to those people and they say, didn't we do this 6 months ago? And no one likes doing the same thing repeatedly when you thought it was a one-time thing. So it's important for us to catch where we might start making IMDSv1 calls earlier. This can look like things like using, I mentioned using Terraform, and you can use things like checkoff to automatically check that Terraform configurations only allow IMDSv2 at the point that users may be making a pull request. We can add safe defaults at multiple layers. AWS supports enforcing IMDSv2 at the machine image layer, as well as region-wide. Similarly, I mentioned using Terraform. It's really common to not have every user write every Terraform auto-scaling group configuration from scratch. You might use things like modules to sort of dry up that configuration. If everybody's using the same auto-scaling group configuration and you're confident that you use AWS IMDSv2 everywhere, you can make that the default in the module, and now everyone who uses that module gets it for free. And even better, your product engineers who don't care about this, they care about making the product better for customers, don't have to think about it. And for me as a person on the platform team, that's the dream. I want to internalize those risk management things, those platform-specific details, and make it so that users actually don't know about this stuff at all. Lastly, you get into monitoring. All systems fail. Every single one of them. I already mentioned, I think I said goofs and not oopsies, but let's call them oopsies. Oopsies happen, regressions happen. Even if we do it at 2 or 3 layers, things can happen where 2 or 3 things fail at once. It's a bummer, but part of life is living with that, and the way we live with that is we monitor for it. We can put in place detections that if we start seeing IMDSv1 calls, we send ourselves a page because we don't believe we live in a world where that should be happening. And if we do, it's an incident because some of our sort of axiomatic beliefs about our environment are clearly untrue, and we need to deal with that. And lastly is sort of the sledgehammer size thing of you can write controllers that look for instances in AWS. Like, who cares what Terraform says? That's a state of truth, but like you can look at the AWS APIs and say, show me the instances that allow IMDSv1, and then automatically terminate them. If you do this when things are still depending on it and don't know that you should be migrating, this may be very disruptive. You may cause incidents. But going back to that, if you live in a world where axiomatically you believe that there is no case for IMDSv1, you've seen your entire fleet running without IMDSv1, it may be safe to go and just terminate any instance using v1. Cool. I'm going to now turbo speed through the Kubernetes pod side of this because it is, like I said, it rhymes heavily and it's very similar. But just for the sake of sort of taking a similar thing but fitting it to the same model, how do we find it for Kubernetes pods? For us, I mentioned we're using a emulation of IMDS. That's code that we operate. So we're able to just dynamically instrument that with metrics that are specific to IMDSv1 that tell us the specific services and pods from the get-go. So in a lot of ways, it's actually easier to find for these. Fixing is exactly the same, right? I mentioned that in all of this, one of the really cool things is most of the clients are AWS SDKs or GCP SDKs, things we don't maintain. So the fixes look the same, regardless of the server implementation. So that's exactly the same, and we can go to remediation. This is an area where actually we had a lot of fun, not in the challenging way I mentioned earlier, but in the fun way, in that because we maintained the code for our Kubernetes layer of IMDS services that we use to distribute AWS credentials and GCP and Azure credentials to all of our pods, we could use an internal feature flagging system that we had at the time to roll it out service by service. And what this let us do was say, we know 95% of services don't use IMDSv1 at all today. So what we're going to do is turn it off by default, except for this exception list of the 20 services or 200, however many it was, that do it. And then we're just going to go through that exception list and service by service remove them. It also let us roll out those service removals sort of data center by data center or region by region. So we're able to quickly set a default where new services, existing services, we could assert that they weren't using IMDSv1 and then burn down the rest as an exception list at the cadence that worked for those service owners. Lastly, again, going back to the difference here is we own the code and we can literally rip out the IMDSv1 support from the emulated server. You can't use IMDSv1 on a server that just doesn't support it. Cool. So zooming all the way back out, I promised at the beginning of the talk we were really talking about, not actually talking about IMDSv1 at all, but we were talking about how do we do fleet-wide migrations on large heterogeneous fleets in non-disruptive ways that are fun for users and platform operators. And so sort of the lessons we learned from looking at IMDSv1 in that is, this is going to sound really stupid, but I'm going to say it, is you have to know what's happening in your environment to be able to change what's happening. The first step, if you go in and say we have to change IMDSv1, you could be talking to an executive, you could be talking to an engineer in a product team, you could be talking to somebody else in your team. Usually the follow-up question is, well, what's using IMDSv1? Anticipating that and having a good view on what's happening in your environment and why, whether it's things like that software catalog or CSM-type security systems, is really crucial to do change. You have to know what you're changing and what your reality is today. Second is turning big migrations into 1,000 little migrations. Big migrations are high risk, high leverage. They tend to fail because they're scary, and it's much harder to accept the risk if we're going to do something everywhere all at once and potentially cause customer-facing outages than it is to say, we're going to do this 1,000 things at a time, and we'll do the first 1, 2, 3, 4, 5 slowly and steadily and learn from it, and then we'll sort of grow exponentially. We'll do them in batches of 10, then 100, and gain confidence over time. Find, fix, remediate, prevent isn't that in and of itself, but using that sort of as a cycle and just like continually applying that as you burn down the list takes a big scary thing and turns it into, I always use a terrible analogy of if you have a plate full of food you got to eat, the order doesn't really matter. And with these big 100% migrations, trying to prioritize what matters, oftentimes there's no money there. The money is in just starting to work through it and learning from it and eating more and more until the plate's empty. Last is that a lot of this was facilitated because we integrate security tooling through every single software delivery lifecycle step. That's from things like those checks I mentioned, which are before they even merge code or make changes. It's catching it when they're trying to deploy. It's those monitoring when things slip at the end of the software delivery lifecycle. There's no one magic point to do this. Security is not a side thing, the same way that I think the industry really evolved where reliability was not like a separate discipline, but was just woven through the fabric of how we build services, how we build technical systems. For these sorts of efforts, security is exactly the same. It is just simply a facet of building successful distributed systems. And that being a facet that you weave through things means you're probably going to have touch points throughout the entire cycle, from the first time someone commits to opening PRs to deploying it to responding to incidents. And meeting people where they are is a big way to be successful with that. So I think we have a bit of time for questions. And yeah, thank you all for attending.
OK, awesome. Does anybody have any questions for Ian? Cool. If not, then I'm going to ask you a question.
Oh, no, I do.
I
was just making my way to the microphone.
Mic, sorry.
It's OK. So we've been dealing with the move from V1 to V2 a little bit. And one of the suggestions when we were setting up our EKS cluster was to increase that hop limit for puts. But I've read some recommendations that that is insecure. So some of the automated tooling might trip that as like a vulnerability. So do you have any insight onto whether Datadog's, or if you know AWS's Security Hub would trip that? Like I've been hesitant to just turn that on because of what I've read.
I don't know precisely offhand. It is in the realm of, like, there's some security things where there's pretty like cut and dry assertions of like, this is safe, this is unsafe. I think with SSRFs and IMDS, because so much of it's a usability trade-off, there is no silver bullet, and like hop limits might be okay if you can make assertions that this isn't a security group that's only accessible from this other security group and things like that. And so I think this is somewhat true to really all security, but really heavily in this area. You may relax one constraint, and it's probably okay if you can say why it's okay because you have other countervailing constraints. As to the question about Security Hub and Datadog, offhand, I don't know where their proclivities are for that.
All right, thank you very much.
Yeah.
We've probably got time for one more, if there's any other questions. Cool. If not, then another round of applause for Ian. Thank you very much.
Thank you, everyone. Appreciate it.